All right, let's jump right in. So often you've got your data, right? You have these specific, solid points that you've measured or calculated. But what about all the empty space between those points? How do you make a really smart, educated guess about the values hiding in those gaps? Well, today, we're going to connect the dots on a really powerful technique called piecewise linear interpolation. So picture this. You've got a set of points just like these. You know the value at point 1, point 2, and so on. But what's the value for any old point in between them? Now, the simplest idea in the world is just to connect the dots. But how you connect them, well, that turns out to be absolutely crucial, and it uncovers some pretty surprising challenges along the way.
Okay, so let's start with what feels most natural, the most intuitive approach. What if we tried to find one single, elegant rule? A single perfect curve that just smoothly passes through every single one of our points.
Now, the fancy term for this is fitting a high-degree polynomial. And really, all it means is you're trying to create one single kind of complex equation that perfectly nails every data point you have. It sounds so sophisticated, right? And in theory, it really should be the perfect solution. But this seemingly elegant approach, it has a dark side.
And that brings us to the villain of our story. Because trying to force one super complicated curve through a bunch of data points, that can lead to some seriously messy, and I mean seriously, unreliable results.
You see, as you add more and more data points, that single polynomial curve has to get more and more complex, what we call high degree. And the math shows that these incredibly twisty-turny equations become extremely sensitive. Even the tiniest rounding error in your calculator, we're talking a number off by a trillionth of a decimal place, can get magnified like crazy and send your final answer completely off the rails, making it totally untrustworthy. And this contrast really gets to the heart of the whole thing. Over on the left, that's our villain, the single complex curve. It's a pain to compute, it's costly, and like we just saw, it can be wildly unreliable. But on the right, that's our hero, connecting the dots with lots of simple, straight lines. It's efficient, it's accurate, and it completely avoids the chaos of those crazy high-degree polynomials. So, let's meet our hero properly. This much smarter approach is called piecewise interpolation, and you can think of it as a classic divide-and-conquer strategy. Instead of trying to wrestle the whole problem at once, we're going to break it into tiny, manageable pieces. So here's the absolute key takeaway. We are no longer looking for one single master equation to rule them all. Nope. Instead, we're going to find a unique, super simple equation for each little segment between two data points. We're breaking a big, complicated problem into a bunch of small, simple ones. And look at that, we're back to our original image. But now, look at it with new eyes. We're not trying to draw some wild, swooping roller coaster of a curve through all these points. Not at all. We're just drawing a straight line from our first point to our second. Then a totally new straight line from that point to the next, and so on. Simple, clean, and incredibly effective.
All right, theory's one thing, but let's see how this actually works in practice. Here's our data set. Pretty straightforward. We know that when x is 1, our function's value is 3. When x is 2, the value is 7, and so on. Our mission, should we choose to accept it, is to figure out the values for x's that aren't on this list. Like, what's the value at x equals 3, or maybe 7?
So, using our piecewise method, we calculate a separate, simple formula for each little segment. For that first piece, between x equals 1 and 2, we find the straight line that connects those 2 points. Turns out that line's equation is 4x minus 1. Then we do it again for the next piece between 2 and 4 and find a completely new line with the rule 7x minus 7. And finally, a third rule for the last segment. Each piece gets its very own simple custom-fit line. Okay, moment of truth. Let's use our brand new set of rules to find a value that wasn't in our original data. What is the value of our function when x is 3? The answer is 14. So how do we get that? Well, the number 3 falls in that interval between 2 and 4. So we just grab the special rule for that specific piece, which was 7x minus 7. We plug in 3, we get 7 times 3, which is 21. Take away 7, and that gives us 14. See how clean and direct that is? No fuss.
Awesome. Let's try it one more time, just to really lock this in. What about the value of the function when x equals 7? Which one of our rules do you think we're going to use for this one? It's 60, exactly. This time, since x equals 7 falls into our last interval, the one between 4 and 8, we use the rule for that piece, 13x minus 31. So we just calculate 13 times 7, that's 91, subtract 31, and boom, we get a solid, reliable estimate of 60.
So what's the really big takeaway here? What's the main idea? It's that in the world of math and data,
Sometimes the simplest, most direct approach isn't just easier, it's actually way more powerful and a whole lot more reliable.
And this is exactly why piecewise interpolation is such a winner. I mean, it completely sidesteps all the drama of those complex curves and their wild, unpredictable rounding errors. It's fast, it's efficient, and it gives us really accurate, trustworthy estimates because it's just focusing on one small piece of the puzzle at a time. It's just a beautiful proof that sometimes the most intelligent solution is to break a huge challenge down into simple, manageable steps.
And that kind of leaves us with a final thought, doesn't it? This core principle of breaking down a big, intimidating problem into a series of small, simple ones, that doesn't just apply to connecting dots on a graph. Where else in our work, or heck, even in our lives, could this piecewise kind of thinking lead to a smarter, more elegant solution?